Okay, so we just saw that set operations are going to be really important. I'm going to back up and just focus on this idea of set operations. So what's going on with set operations? So the idea is, for right now, we're just going to focus on Venn diagrams and some basic ideas. And the reason I'm using Venn diagrams is just easier. So even though tree diagrams are still valid, this is just a little nicer. So suppose I've got my sample space. This is everything that can happen. I've got a set of events called A and a set of events we'll call B. And if I want to talk about A union B, this is everything in A or things in B. So if you give me something in this set A union B, that means it could be either in A or B. And notice it could be in both. So we've got to be a little careful. I'm going to have the complement. So your authors say AC. Some authors write it as a hat over the A, or sorry, a bar over the A. So this is the complement of A, and this is the stuff not in A. And then finally we're going to have A minus B. So this is the stuff in A that's not in B. And I can write this as A and B complement. So why is that? So if this is A and this is B, the complement of B is everything not in B. It's everything outside there. And what's in A is in here, plus this. But if I take the complement of the stuff on the outside, I end up excluding that, and I'm only working with that set right there. And so anything in here is in A, but it's also outside of B. All right, so there's all kinds of nice things we can do. So for example, we've alluded to this. If I've got a bunch of sets and they're disjoint, and this is, I can't emphasize enough how important that is. Later on, very soon, we're going to just have to figure out a way to get around this, because this rarely happens in real life. But if those things are disjoint, then the probability that A1 happens, A2 happens, or A3, or any of these things is going to be the sum of probability of A1 plus probability of A2 all the way out to the end. So the question is why is that? So again, we're going back to this idea that we are assuming we have these disjoint sets whose union is the sample space and their disjoint. So if that's the case, I'm going to assume that A1 is some union of these things. So we'll assume that this is some union of these W1I's. A2 is also going to be some union. W2J. So that's it. And the key things is that these are different W's, and they have to be different because these sets are disjoint. And so each of these sets I can write as a union of different base events W. And because of that, now if I want to look at the probability of A1 plus probability of A2 on out to the probability of AM, probability of A1 now is going to be the probability of the unions of the W1I. Probability of A2 is the probability of the union, the W2Js, and you can keep doing that all the way out to the AM, and that's going to be the union of the MKs, and then by definition, because these are base sets, this is going to be the sum of the probability of the W1Is plus the sum of the W2Js. And this keeps on going down to the very end. It's going to be the sum of the WMKs. And now I can pull all these together in terms of one big huge sum. Blah, blah, blah. And I take all of these sums together. This is going to be equal to the probability of the union of all of these W's, because all of these W's are disjoint, because the A's are disjoint. And now this becomes this union over Ij, Wij. And then from the definition of these, this is just going to be the probability of the union of A1, A2, A3 to we called it M. Okay, so we have that the probability of this is equal to the probability of the individual A's. And again, this all comes from assuming things are disjoint. All right. So what? Well, one nice result from this is I can say, suppose I've got A1, A2 to AM, and suppose S is the union of all those things, and these A's are disjoint. So that means if you give me a set E, I can write E as E intersected with the set of all possibilities, so E and the sample space. I just said I can write the sample space as A1 union A2 union A3 out to AM. So be careful, this is intersection. So this becomes E in the intersection of A1 union E in the intersection of A2 union E in the intersection of A3, and this just keeps going on until I get E in the intersection of AM. So this means that the probability of E is going to be probability of E and A1 union E and A2. This goes all the way down to E and AM. I claim these are all disjoint. Why are they disjoint? If I take E and AI and intersect it with E and AJ, so I is not equal to J, this is the same thing as E and AI and E and AJ, but E and E is just E. So this becomes E and AI and AJ. Well, the intersection of AI and AJ is the empty set, and E in the empty set is just the empty set. So these are all disjoint. So that means then, so we have the probability of E is equal to the probability of A1 and E union A2 and E, and this goes all the way out to AM and E. Since each of those things are disjoint, I can write this as probability of A1 and E plus probability of A2 and E, and on out to AM and E. Okay. So that's a fun result. It's nice. This is oftentimes used in practice in that if you don't like decomposing in terms of the W's, you can just find any other decomposition that you can write in terms of the W's, and that's still going to work and serve the same purpose. This is going to lead us to a really important theorem. This is 1.4 in the book. And suppose we have two sets, A and B, and those two sets are subsets of our sample space. I do not have a general formula for this, but just intuitively, what do we expect to get? Well, if I look at that, that's going to be the probability of A. If I look at this, that's going to be the probability of B. But notice, I added that up twice. That goes in probability of A, and that goes in probability of B. So I should probably subtract off the extra piece. So the question is it true? And the answer is yes. So let's see if we can show that for real. So the claim is probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And so what are we going to do? So we've got our two sets. Now notice the probability of A or B is going to basically be A, B, but I got to be careful with this. And the only result I have is how to deal with disjoint sets. So what I'm going to do is I'm going to break this up into three pieces. A, but not B. Oops. Let's do this. And then B, but not A. And then the stuff in there. And now if I can write it like that, so A or B is the probability of A but not B, or A and B, or B and not A. So let's see. So probability of A and not B is going to be A and B complement, or A and B, or B and A complement. And now these are disjoint sets. So I can write this as A and B complement plus probability of A and B plus the probability of B and A complement. So now the question is how the heck do I get those things? And here's the thing to notice. Probability of A, that's going to be the probability of A and B complement, or A and B. Because it could be either outside A and outside of B, or in both. These things are now disjoint sets. So that's the probability of A and B complement plus the probability of A and B. So now solving for that term, that's probability of A and B complement is the probability of A minus the probability of A and B. And I'm going to do the exact same thing with B. Probability of B, well, I can be in B and not A, so that gives me the stuff in here. Oops, got to be careful here. Let me rewrite that. I could be in B and not A, or I could be in A and B. And notice these two sets are disjoint because it's basically this set in here in red, it's in both, or the stuff that's in B but not A. So I can use our previous results. So that's the probability of B and A complement plus the probability of A and B. And now solving for that, which is here, the probability of B and AC is the probability of B minus the probability of A and B. So from above, I have probability of A or B is the probability of A and B complement plus the probability of A and B plus the probability of B and A complement. And we just said probability of A and B complement is probability of A minus the probability of A and B plus the probability of A and B, and the probability of B and A complement is the probability of B minus the probability of A and B. So this becomes the probability of A plus the probability of B, then minus the probability of A and B plus the probability of A and B minus the probability of A and B is minus the probability of A and B. Okay, so that was a ride. So our intuition is right here, but notice trying to show that and demonstrating that our intuition is correct is a bit of a ride. It's not so simple, and we've got to be really careful about our set operations. And really, the only tool we have is this idea that we can break apart the probabilities when we have disjoint sets. Okay. But this new tool here is going to be something else that's going to allow us to expand things and work in that direction. So let's look at some examples. Let's take a fair six-sided die, and I'm going to roll it twice, and I'm going to add up the results. Okay. So I'm going to ask questions about the probability of this. Before I do anything, I really should just stop and try to break this up into pieces. Okay, so what I'm going to do is look what happens if I roll a 1, 2, 3, 4, 5, or 6 first. And then second, I could do a 1, 2, 3, 4, 5, or 6. So this is my sample space. And this is now a Venn diagram of my sample space. And so this right here means I rolled a 2 and then a 4. In terms of the random variable I now have, the random variable is a sum. So this will be a 2, 3, 4, 5, 6, 7. It's going to be 3, 4, 5, 6, 7, 8. And I can fill out the rest. And notice the way I did this, because I'm assuming it's a fair die. All these, the first rolls are equally likely. Second roll, all those are equally likely. So each of these events, each of these things in these little squares represents one of my W's. If they're the same, and there's 36 of them, the probability of any one of those things has to be 1 over 36. Okay. So I can ask, what's the probability that the sum is less than or equal to 4? Well, that could be here, 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 here. So that's 1, 2, 3, 4, 5, 6 of those things. Is that right? Yeah. Notice if I ask what's the probability the sum is strictly less than 4, it's going to be either 2, 1, 1, 3, or 1, 1. And that's going to be 3 out of 36. Okay. What's the probability I get an odd sum or the sum is less than 4? Well, I could just look at this and say, oh, that's going to be odd. There's going to be, half of these, so 18 out of the 36. But then I'm going to have to add this situation here, because that's not accounted for. So that's going to be, 19 out of 36. But I also know that I could look at this as the probability I get an odd sum plus the probability the sum is less than 4 But then I'm going to have to subtract the probability it's an odd sum and the sum is less than 4. So if I do that, the probability that it's odd, that's going to be 18 out of the 36. Probability the sum is less than 4 is going to be the 3 out of the 36. And the probability that the sum is odd and the sum is less than 4 is basically that. So that's going to be 1 over 36. And when I add those, sorry, that's wrong. If the sum is odd and the sum is less than 4, that's these two. That's going to be minus 2 over 36. Gives me 19 out of 36. I get the same answer. Okay. I'm going to do one last example and then I'll introduce some new notation. This is a really important idea. What's the probability the first roll is odd or the sum is even? So let me look at my sample space. So we've seen this many times. I'm just going to write this down. So this is going to be what? 1 and 1. So there's my sample space. So if the first roll is odd, that means I roll a 1, 3, or 5. So that would basically be this event in my Venn diagram. So the probability first roll is odd. It's going to have 1, 2, 3, 4, 5, 6, 12, 18. That's 18 out of the 36. Probability the sum is even. That's going to basically be this. 2, 4, 6, 4, 6, 8, 4, 6, 8, 6, 8, 10, 6, 8, 10, 8, 10, 12. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's going to be 18 out of 36. So the probability the first roll is odd or sum is even is going to be the probability the first is odd plus the probability the sum is even minus the probability the first is odd and the sum is even. So how can they both be odd and how can they both have first odd and the sum even? Well, this is going to be first is odd and even, and this one, and then down here, it's going to be odd and even, and then the same thing here. So there's 9 ways that can happen. So this is going to be 18 out of 36 plus 18 out of 36. Minus 9 out of 36, and that's going to be what? 36 minus 9 is 27 out of 36. All right. What if I happen to know that the sum is greater than or equal to 4? How does this change? Well, this changes in that my sample space is different. So what I have before This is what my sample space before looked like this. These are all the things that could happen, and I've decomposed this into sets of events that are disjoint and equally likely. And I did this because it's just more convenient to think about it in this way. But if I know that the sum is greater than or equal to 4, that means it could not be 2. I could not have rolled a 1 and a 1. I could not have rolled a 1 and a 2. And I could not have rolled a 2 and a 1. So for my sample space, those are out. That doesn't work. So really what I have now for my sample space is something like this. So I'm going to be careful here. So I could have gotten a 4. I could have gotten a 4, 5, 6, or 7. So I could have gotten any of these things. So this would be 4, 5, 6, or 7. So now in terms of what has happened, so if I'm given that the sum is greater than or equal to 4, this is now my sample space. The situation where I did 2 1s or a 1 and a 2 and a 2 and a 1, I know can't have happened. So now my sample space looks like this. And if I want to know what's the probability I get first roll odd or the sum is even, given that the sum is greater than or equal to 4, this is basically going to be, let's see, so this was 1, 2, 3, 4, 5, 6. So this is going to be basically all of these. And then in terms of even, I could be here. Be careful here. So 4, 6, 8, 6, 8, 10, 6, 8, 10, 8, 10, 12. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 25 ways that could happen, and if I'm assuming each thing is equally likely, my probability now is 25 out of 33. So this idea that if you have information, we need to incorporate new information. This is called conditional probability. And the idea is that I want to know what's the probability that E occurs given that I know C occurred. The notation here is going to be the probability of E, and we use a vertical bar C. And it's pronounced the probability of E, I might say E occurring, but this bar is pronounced given C. Oops. Okay. And so what we had before was the probability of first roll odd or sum even, that's my E in this case, given the sum is greater than or equal to 4.